Okay, so last time we were looking at CTL model checking. So we said that CTL model checking is in P time, whereas LTL model checking is P space complete. Okay, and we also looked at several properties which can be expressed using CTL but not in LTL, and there can be properties that can be expressed in LTL but not in CTL, vice versa, right? So, um, and there is also this one result which we discussed without proof, which is like that if there is a CTL formula, then you can consider an LTL formula which can be removed by obtaining, by eliminating all the path quantifiers from the CTL formula, and then uh, it's like these two should either be equivalent, like the one that you obtain from here by removing all the path quantifiers. So they are either, I mean, so either the CTL formula is equivalent to this LTL formula that is obtained from by removing the path quantifiers, or there doesn't exist any such LTL formula that is equivalent to this file. So now, one of the things which we saw is like, okay, this LTL formula is p-space complete, right? And whereas LTL model checking is p-space complete, whereas CTL model checking is in polynomial time. And the thing is that it's not quite the case that CTL model checking is sort of easier. It's more like sometimes it may be the case that some formulas in LTL, the properties in LTL, it can be expressed in a more succinct way. So the LTL formula can be more succinct. So what are we saying? So for example, like a CTL formula uh, can be obtained, like if you have a CTL formula, let's say of phi, and then you have the LTL formula tau. Now, one thing is there that since we are removing all the path quantifiers, so the size of the CTL uh, formula is at least as big as the one which is as big as the LTL formula. Okay. But now the question is that how big can this be? So there can indeed also be properties where the CTL formula is exponentially larger. Okay, the CTL formula can be exponentially larger. So, for example, like, so you can have a CTL formula, which is, let's say, so what I'm saying is that there can be properties for which, and for which both LTL and CTL formula exist, but uh, the LTL formula, I mean, an LTL formula may exist, an LTL formula may exist and is exponentially more succinct. Okay, so essentially what it says is that, like if you are given a CTL formula, there may be a CTL formula. Now, if you remove the path quantifiers, you may get also an equivalent LTL formula, but there may also exist other LTL formulas which may be exponentially more succinct. Okay, so if they are equivalent, like this particular result says that if I give you a large, let's say CTL formula, which is large enough, you remove the path quantifiers, you may get an LTL formula, which is equivalent. But then there may also exist other LTL formulas which are exponentially more succinct. Okay. So an example is, for example, you can try to, let's say in a graph, in a transition system, if you consider the existence or non-existence of a Hamiltonian path. Okay, you know what a Hamiltonian path is. So non-existence of a Hamiltonian path that you can express using an LTL formula of polynomial size, polynomial in the number of vertices or linear in the number of vertices of the graph. But then one can show that indeed any CTL formula to express that non-existence of the Hamiltonian path is indeed exponentially much larger. Okay, so the thing is that, like, if you had, let's say, a formula, CTL formula for expressing no Hamiltonian path, okay, and which is polynomial in size of the number of the size of the graph, and given that CTL model checking is in polynomial time, right? What you could do is, like, I mean, you could have solved, I mean, had there been a CTL formula of small size, you could have essentially obtained a solution to the Hamiltonian path in polynomial time, which we know that is not the case unless p equal to NP, right? So that somehow gives also an intuition as to why a CTL formula is can be much more larger. Whereas you can, I mean, if you are given a transition system, I mean, and then, like, given, for example, a graph, you can construct easily a transition system and an LTL formula which will show the absence of a Hamiltonian path. And this LTL formula is much like just linear in the size of the graph. Okay, this is something you can try. So is it clear for the online participants what I said just now?
Yes, sir.
Yeah.
Okay. Okay, good. So right. Um, and so we last time we saw such examples like this formula for all paths, eventually for all paths globally A, and the LTL formula which you obtain by removing the path quantifiers, they are not equivalent. We saw such examples, and similarly for such a CTL formula, again, like if you remove the path quantifier here, then the resultant LTL formula, they are not quite equivalent. Okay. And then we also talked about CTL star, and we said that CTL star strictly encompasses both LTL as well as CTL, and the model checking for this is also the same as that of LTL model checking. Okay. So in CTL star, the syntax is essentially, it relaxes that alternation requirement that you have in CTL. Okay, so that in CTL star will relax. Okay, and any CTL formula is also a CTL star formula. Any LTL formula has an equivalent CTL star formula of the form for all signs. Okay, and this is what we mentioned. CTL star is strictly more expressive than LTL as well as than CTL. Okay, good. So today we are going to talk about bisimulation. So what is the idea of bisimulation? So you have studied language equivalence. So for example, or trace equivalence in the case of two click structure. If there are two systems, trace equivalence or language equivalence, they talk about some kind of equivalence properties between two systems. Okay. And bisimulation is something which is a stronger notion of equivalence in the sense that if two states or if two click structures, if they are bisimilar, then they are also language equivalent, but it's not necessarily the other way around. Okay. So bisimulation, it's it's a concept. I think again it was in the early 80s. It was proposed by somebody called Park, and then it was popularized in computer science by Robin Milner. So Robin Milner was again another Turing laureate who did pioneering work in functional programming languages, and then also something called uh, process calculus. It's like how different processes which are concurrently executing, how they behave, and there is an algebra among such processes and things like that. And so he also studied bisimulation in the context of this process algebra called the calculus for communicating systems. So you can also look for calculus for communicating systems. Communicating systems, and this was by Robin Milner. Okay, so let's see what is a bisimulation. Okay, and let's consider a three-case structure, which is of this form that you have a set of words. W0 is a set of initial words, and then you have like E is the edge relation among the words, and L is the labeling function, right? So I'm sometimes also using this as yeah, capital L here. Okay. So it's a binary relation, okay? By simulation relation, it's a binary relation which relates a pair of states, okay? And how is this related? Like, so for all S1 comma S2 belonging to this relation R. So I'm defining the bisimulation relation R, okay? How is the bisimulation relation R defined? So for all uh, pairs such that S1 is related to S2 through this bisimulation relation R, and it's kind of again recursively defined. So first of all is like the set of atomic propositions that you have in S1 and the set of atomic propositions that you have in S2, they have to match first of all. Okay, so this is this thing. Then just look at this. So it says that for all successors, so suppose S1 you have different successors, right? S1 can have different successors. So these successors, I call them S1 prime. So for all such S1 prime successors, there should exist a successor S2 prime. So if S1 and S2 are related, if S1 and S2 are related, so for all successors here, so there is a quantifier here, right? Like a for all, and then there is a quantifier alternation there exists. So for all S1 prime, there should exist an S2 prime. Okay, S2 prime belonging to the uh, like one of, I mean, set of successors of S2. So S2 prime should be a successor of S2 such that S1 prime and S2 prime are also related. Okay, so it's recursively defined. So you say that S1 and S2 are related if for all successors of S1, that is for all successors S1 prime, there should exist something an S2 prime such that S1 prime and S2 prime are related. And similarly, the other way around works. For all successors S2 prime, right? For all successors S2 prime of S2, on this side also there should be an S1 prime such that S1 prime and S2 prime are related. Okay. So these are the two directions. Okay. And as I say that S1 and S2, they have the same set of atomic configurations. Right. Now you can also, so these are, you say like, so these S1 and S2 are two states in the same case structure. Okay. But you can also try to talk about uh, that whether two different Kripke structures are bisimilar. Okay, if you want to talk about two different Kripke structures, they are bisimilar, then you have to somehow equate or relate their initial states. Okay. So for all, so then it's like for all initial state in one grid structure, there should exist another initial state. There should exist an initial state in the the second grid structure, and so on. That so that they should be related. So in addition, you also need that because you are talking about two grid structures which are being like related. Okay, so you talk about their initial states. And these are, I mean, in essence, they are not very different. Like you talk about two states of the same Kripke structure or two states of two different Kripke structure, whether they are bisimilar. I mean, they are, in essence, they are the same. It's the same thing. Okay. So we say that S1 then tilde S2 if there exists a bisimulation relation R such that S1 comma S2 belongs to. Is it clear? The definition is clear. The definition of the bisimulation relation. It will become, I mean, you think that it's clear, but it's actually, we see that it requires a bit more intuition and clarity. I mean, once we discuss more. Okay. Now, the largest bisimulation relation. So this we also denote with the largest as the largest bisimulation relation. This is also called a bisimilarity relation. Okay, so bisimilarity relation is the one which is the largest bisimulation relation, and in fact, one can show that this is indeed the union of all bisimulation relations. Okay, you can take the union over all bisimulation relations, and that is what is called the bisimilarity relation. Okay, so now suppose I want to show. For example, if I want to show that S and T, whether they are bisimilar, what we need to do in order to do so, to show that S and T are bisimilar, we need to define a bisimulation relation. Okay, so you see here I write something called a strong bisimulation. So I'll say a bit about it, what is strong and what is weak. But right now, whenever we just talk about bisimulation, it is essentially a strong bisimulation relation. Okay? So, yeah. So, in order to show that, let's say, state S and state T are bisimilar, we have to construct a bisimulation relation. So, how do you construct a bisimulation relation? So, you have to do this recursively, right? So, for example, here you can see that um, so you have to construct this relation. So like you have uh, so how was it defined? Like you see that for all successors you have to find some match from the other side, right? So this is what we have been doing. Like so in order to say that if S and T they belong to the relation R, which is a bisimulation relation, then for all successors of S, right, like which are S1 and S2, I have to find a match on the other side. And similarly, for all successors of T, I have to find a match on the other side, like this. And indeed, we can show that here, if you see, that here you have PQ, here you have PQ. So, right, this is PQ here, the atomic propositions. Here also you have atomic propositions PQ. Whereas on this side, you have R and R. These are the atomic propositions, right? So we need to define a strong bisimulation relation. So I define it in this way, ST. Then I have S1, also S1 matches with T1, and also I have S2 also matches with T1. Okay. And this is recursively. I don't need to, once I have S1 T1 and then S2 T1, after that there is a self loop. Okay. So I don't need to add any more state, any more pair. Okay. So, and this is my bisimulation relation. Good. So now what is the notion of a strong bisimulation relation? If I'm talking about something strong, then there must be a notion of a weak. So the idea of a weak bisimulation relation, it possibly makes more sense when you, or maybe, yeah, even in the cricket structures also, like sometimes you say that there are some invisible transitions, like, or some states where you have some kind of, like, there is a notion of observation. Notion of observation. Okay. So sometimes what can happen is like uh, you may have some successor, but the successor state you cannot really observe. Okay. So you can have, let's say, there is on one side, you can see an A here. Maybe there is a B here you observe, like on one side. On the other side, you may not observe anything, like which I represent by a tau to denote that you are not observing anything. So if you have an A, then there is some, this is called a stuttering, like, so essentially you are not observing anything, but then after a while you observe the B. Okay. So this is called a weak bisimulation. So where it depends on what is observed. Like, I mean, as if like these taus are internal transitions. They correspond to internal states. So you don't observe them. Whereas strong bisimulation, everything is observable. Like you can observe each step. Okay. So this is the notion of a weak bisimulation. And as you know, a strong always uh, indicates like it implies a weak thing always. So strong bisimilation implies a weak thing. If they're strongly, if two things are strongly bisimilar, they're also weakly bisimilar, but may not be the other way. But so right now, for this course, we will only be like looking at the strong bisimulation. So whenever we are going to talk about bisimulation, it's a strong bisimulation we're talking about. Okay. Good. So now, just one thing we should maybe take note of is that it's this relation, the strong bisimilarity relation. This is an equivalence relation. Okay, this is an equivalence relation. Uh, so why? Because suppose you consider this. So what is an equivalence relation? It is reflexive, it's symmetric, and it's transitive, right? So if you consider, let's say, a relation R of the form S comma S, then you can, of course, show that this is indeed um, this. If you just consider this reflexive relation, and it is indeed a bisimulation uh, relation. Okay. So why is it so? Because suppose if you are in this S comma S, so of course L of S equal to L of S on the two sides, right? So these two sides. And then like for every successor, there you can also consider the same pair, right? Like from S you consider the successor T, here also you will consider the successor T, and T comma T will also be in the, is also in this relation R, right? T comma T is also in the relation R. I mean, if you recall the way it is defined, that your S1 prime, S2 prime also have to belong to R, right? So, so it's reflexive. And similarly, you can also uh, define that it's symmetric in the sense that if, let's say, if R be a bisimulation relation, then you can define this the symmetric relation, which is S2 comma S1. Okay. And when S1 comma S2 belongs to R. Okay. And this also you can show that this is a bisimulation relation. Right. If you have say a relation R where S1 comma S2 belongs to R, then you can define the relation R inverse, which is like S2 comma S1, and this is also a bisimulation. And you can also talk about transitivity, right? So how are you going to define transitivity? So essentially, like, you can define a relation R. Okay, so we were saying that the strong bisimilarity is an equivalence relation. So indeed, we saw that it is reflexive as well as it is symmetric. And we also want to show that this is transitive, right? So in order to show that this is transitive, So we can again construct a relation which is of the form like this S1 comma S3 such that there exists a state or world S2 such that S1 S2 belongs to some bisimulation relation R12 and S2 S3 belongs to some bisimulation relation R23. Okay, and now uh, we should be able to prove that indeed this relation R, the way we have uh, constructed here, right? This is also, right? So this is the way we have constructed R. This R is also a bisimulation relation. So why should it be the case? Why should this R be a bisimulation relation? Can someone say?
So the language of S1 and language of S3 will be same.
Sorry, what of S1 and S3?
The L of S1 and L of S3.
It's not the language, it's the label of S1 and the label of.
Sorry. Yeah.
Mhm.
Yeah, that will be the same. And then for any successor of S1,
S1 goes to some successor S1 prime, right?
yeah.
Yeah.
Then we know there is a successor of S2,
Ah,
which is S2 prime,
ah,
such that S1 prime and S2 prime are
yeah.
equivalent. Some such.
Yeah, S1 prime, S2 prime belongs to R1, 2. And then similarly, because you have this, and you also have that from S3, you can go to S3 prime such that S2 prime and S3 prime belong to R2, 3.
Yeah.
So since S2, S3 belong to R2, 3, so S2 goes to S2 prime. So there should be an S3 prime such that S2 prime, S3 prime belong to R2, 3. And if that is the case, then it also gives us that S1 prime, S3 prime, right? From these two,
Yeah.
you get S1 prime, S3 prime. They belong to uh,
R.
R. Okay, and you have that. So this gives that R is the bisimulation relation. Is it okay? Right?
Yeah. Yeah.
Okay. So now I define something called a path bisimulation. So this is the strong bisimulation that we define. Now I define something called a path bisimulation. So the idea is the following, that I define the path bisimulation relation as R, and again R is a subset of W cross W. We say that S1 comma S2 belongs to R if all the conditions are similar, like LS1 equal to LS2, and now instead of just one looking at only the successor, here, I mean, unlike standard bisimulation, here we will be looking at paths of arbitrary length. Okay, paths, finite paths of arbitrary length. So you can talk about for uh, for all paths pi belonging to paths of S1. Paths of S1 is a set of paths. Uh, I mean, we can talk about, let's say, finite paths or infinite paths. Uh, and if I talk about, let's say, pi here is a finite path, then um, there exists uh, a path um, pi 2 belonging to paths of S2 such that um, from S1, you can like essentially following that path pi 1, you reach S1 prime, and following the path pi 2, you reach S2 prime from S2, and S1 prime, S2 prime belongs to R, and similarly the other way around for all paths pi 2 belonging to paths of S2, there exists a path pi 1 belonging to paths of S1 such that S1 goes to S1 prime and S2 also goes to S2 prime, and S1 prime, S2 prime belongs to R. Okay, so this is called the path by simulation. And what we would like to state here is that a relation R is a bisimulation if and only if it is a path bisimulation. Is it clear? The definition of the path bisimulation, and then essentially this the statement of the theorem. Is it okay?
Yeah.
Yeah, right. And now, how do you prove such a thing? Which side is easy? Let's say the proof. How do you prove this?
So
That
if it is a bisimulation, it is also a path bisimulation.
path by simulation implies by simulation. This side is, I mean, both are not, none of them is difficult, but yeah, if I look at start with this direction, path by simulation is a by simulation, then why is it true? Why is it true?
So can we say, like, suppose there is a path by simulation, then take the single length path. Then we
Single,
want to show that the corresponding path from S2 will also be a single length path.
single length path, yes. So, yeah. So, in fact, I think I should have, sorry, yeah, in fact, this, the length should have been part of the definition. There exists a, um, um, mm, 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 mm. So I think here I should indeed talk about path pi 2 such that um, such that pi 2, the length of the paths are the same. Okay, here also the lengths of the paths are the same. So it's like at, so when I talk about for all paths, right, for all such paths, so essentially if you start from S1 and S2, right, at, it's like at every state in the path, because I talk about there is a for all quantification on the paths, I also have the following, that I have at every, for every path here pi 1 here and you have pi 2 here. So at every place, like in here, at every intermediate points, these are also bisimilar, right? They are also path bisimilar because there is a quantification over all paths, right? So a path can be of length 1, path can be of length 2, path can be of length 3, and so on, right? And as Chandralekha was saying, that essentially if you make your path by simulation, if you restrict to paths of length 1, then you get by simulation. Is it clear? Is it okay?
Yeah, makes sense.
right? So if you just talk about path by simulation, if you restrict to paths of length 1, essentially you get by simulation. So this direction is fairly, I think, straightforward. Okay. So what about the other direction? Like if you have by simulation implies path by simulation. So how do you prove such a thing?
Some induction, because every state which is a successor, from there, if you consider the bisimulation relation.
Induction over length of path. Okay, so I can just say that initially, suppose by simulation implies, suppose by, I mean, the best case is by simulation implies path by simulation for paths of length 1, right? So paths of length 1 is the base case. Clear? So is the base case. Now suppose you can make a hypothesis, induction hypothesis, which says that indeed, suppose up to paths of length k, if it's bisimilar, if the relation R holds, then it also holds for paths of length here, some k, right? Paths of length k. And suppose by simulation implies path by simulation for paths of length k, and then we can prove it for paths of length k plus 1, correct? So paths of length k plus 1, right? So how do you prove this? Like, so suppose you consider S1 and S2, and then you talk about paths of length k plus 1, you go to, you take k steps, and then you talk about k plus 1, right? So here you have k plus 1 in total, and here you have up to k. So now you look at some state here. So you consider a path pi 1 of length k plus 1, and after k steps, suppose from S1, you go to a state S1k, okay? And then by the induction hypothesis, you should also have something like an S2k, right? Such that, so what are we saying? Like we are saying if they are bisimilar, then these two are path bisimilar, right? Like, so essentially, like I'm talking about, like if they are bisimilar, then I can talk about S1k and S2k. So they are also so they are also bisimilar, right? And okay, so suppose mm, mm, right. So I'm saying that if this relation R, right, where S1 comma S2 they belong to R, it's a bisimulation relation. We are trying to say that R is also a path bisimulation. Yeah, right. This is what we are trying to say. Now, mm, So okay, and if I talk about paths of length k, suppose this is true, then S1k, S2k, suppose after I consider a path of length k, so I'm reaching S1k, and then there exists something like an S2k, such that S1k comma S2k, they belong to R, right? Okay, S1k, S2k belong to R. So this is by the induction hypothesis. Okay, now if S1k and S2k, so R by assumption, this is a bisimulation relation. Okay, yeah. By assumption, this is a bisimulation relation. And from the induction hypothesis, we also have like paths of length k. So we have S1k comma S2k. They also belong to, this pair belongs to R. And now, since this is a bisimulation relation, we have from S1k, I can have a successor which is S1k plus 1, and then from S2, I will have a successor which is of the form S2k plus 1, such that S1k plus 1, S2k plus 1, they belong to R. Okay. Hence, I have this for path of length k plus 1. Okay. And hence, this gives that a bisimulation also implies path bisimulation. Is it okay? Is it clear?
Yes, sir.
Okay, so this is essentially the proof. So in some places, the path bisimulation is also called a string bisimulation, because I mean, if you talk about, let's say, a transition system where, or maybe let's say if you are talking about two automata, okay, let's see. So you are talking about, here we are talking about Kripke structures, right? So here we are talking about Kripke structure, and then we are talking about the label of the states is the same as the I mean the label of the other state. Label of state S1 is the same as the label of the state S2. But one can also define instead of Kripke structures the bisimulation on some kind of an automaton where you have the labels are on the transitions, right? You have the labels are on the transitions, okay? So how will you define the bisimulation relation there if instead of states, the labels are on the transitions, you say that S1 comma S2, it belongs to R if for all A transitions, or for all S1, S2, for all such transitions, there exists, sorry, S1 to S1 prime, there exists a transition from S2. There exists a transition S2A, S2 prime, such that S1 prime, S2 prime belongs to R. And similarly, for all S2A, S2 prime, there exists a transition S1A, S1 prime, such that S1 prime, S2 prime belongs to R. Okay, is it clear? Like, so, I mean, when we are talking about two automata or two transition systems where the labels are on the transitions instead of on the states, then you can define bisimulation in this way. Okay, so that's the thing. And now, if you consider, let's say, something similar to a path bisimulation, then you will say that I can consider a sequence of transitions. So I can consider a sequence of transitions like you have some, right? Like, so you have A1, A2, A3, etc., A4, some AN like this, right? And I can call, suppose X is a string, which is of the form A1, A2, blah, 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 AN. So X is a string, right? So that's why now we will say, well, I will talk about exactly the same thing. But instead of a single transition, I'll now talk about the sequence of transitions. Okay, so here I'll talk about such sequence X, which is a string, right? And hence it's also called a string bisimulation, which is the same as a path bisimulation as we are talking about here. Okay, any question? Any question?
No, sir.
Okay, good. Okay, so now what is a trace in a Kripke structure? A trace is essentially you have a run, and so in a Kripke structure you have, suppose, a run, right? Which can, an execution of the Kripke structure, a run will look like some W. So you start with some word, let's say W0, W1, W2. This is how an infinite run will look like. And a trace is essentially L of W0, A corresponding to this run, it's L of W1, L of W2, like this, right? Now, this particular theorem states that if K1 and K2 are bisimilar, okay, they are related with some bisimulation relation. Recall that K1 and K2, we are saying they are bisimilar if there exists a bisimulation relation and there is some initial state of K1, right, which is bisimilar to some initial state of K2. So for, I mean, it's not, okay, let me talk about the quantifier a bit clearly. So for every initial state, right, for every W belonging to W01, there should exist some W2 belonging to W02, right, such that W1 and W2 are bisimilar, and similarly for all W2 belonging to W02, there should exist a W1 such that right, such that W1, W2 are bisimilar, right? So this is the thing, there should exist some relation R and such that some bisimulation relation R such that this holds, right? So then we say that the two Kripke structures are bisimilar. Clear? So now we say that if they're bisimilar, then their traces are the same. How do you prove such a thing? How do you prove such a thing? Is the question clear? Is the statement of the theorem?
Yes, sir.
Right. So how do you prove this? So they're saying that if the two Kripke structures, if they are bisimilar, and the definition of two Kripke structure being bisimilar is something that we said here, right? Like if these two Kripke structures, they are bisimilar, then the set of traces of the two Kripke structures are the same. And what is a trace? The trace is the sequence of the labels that you have. Essentially, this is also called the computation of the, it's like the computation of the, one computation of the Kripke structure corresponding to that execution, right? Computation of the Kripke structure. Clear? So you say that the sets of computations, the set of computations of K1 and the set of computations of K2, they are the same. If they are bisimilar, then this holds true. How will you prove such a thing?
So we can consider the start state and path bisimilarity from.
You can consider the start states and the path bisimilarity, right? You can just consider the path bisimilarity. So you consider any path you consider any path of K1, right? For every path of K1, there should exist a path of K2, right? Such that the path bisimulation says this thing, right? Like that indeed, like all these things, they have to be bisimilar at individual the intermediate steps, correct? So you consider the path, and then given that we have the path bisimilarity, it also says that at all the intermediate points, like if you take a long path, it also says that because the path bisimulation is defined over all paths, right? Over all paths, it also gives you that uh, gives you the fact that essentially the labels for every individual for every individual paths over all the intermediate points, they are the same, and the labels essentially give you the computations of the traces, right? So that gives like that the traces are the set of traces of the two Kripke structures are essentially the same, right? Every for every path from K1, there should exist, right? For all path pi 1 belong from the starting from an initial state of K1, there exists some pi 2, which corresponds to that pi 1 such that the computations of the two paths are the same, right? And vice versa, right? Hence, like if I look at the traces of the two Kripke structures, they are essentially the same. Is it okay? Any question? Is that
No, it's clear.
Yes, sir, clear.
clear? Okay, good. Okay, so now we are going to define something called, I showed just one example, which is like two structures are bisimilar, but we have not yet seen something where two structures are not bisimilar. I mean, an interesting question here would be like, what about the other direction? That given that we are talking about if they're bisimilar, then they are trace equivalent. What about the other direction? If they are trace equivalent, then is it necessary that they are bisimilar? The answer is not. And then in that case, we should be able to find two such Kripke structures where the traces are the same, but they are not bisimilar, right? So we'll see that in a while. Okay, now what is the notion of a bisimulation quotient? So what is the idea of a quotient of a structure? In general, when you talk about quotient of a structure, like quotient of a group or anything, some kind of a structure, what is the idea of the quotient here? So in the case of bisimulation quotient, it's like you see that in a given Kripke structure, what are the set of states, right, or the set of worlds that are bisimilar to each other, okay? And then you take them together, okay? You make the equivalence, you consider the equivalence classes, okay? You consider the equivalence classes, and by merging them together, the reduced transition structure that you get is actually a bisimulation quotient of the given Kripke structure of the transition system, okay? So where what is this? Like I can say, for example, so W, this is the set of, it's the, I'll talk about like, it's the set of equivalence classes, like, how do I say this? So I will say is the set of equivalence classes of this. Okay. Right. Okay. And W0 prime is like so essentially it's the set of I'll say S0. So this is like the class of S0 such that S0 belongs to W0. Okay. So this is by this I denote an equivalence class which contains S0 and W0. Okay. And how is R prime defined? R prime is some, let's say, some S to S prime such that S comma S prime belongs to R. Okay. And L prime is a function which is now from the set to the set of atomic propositions. Well, it is like this. Okay. And this is defined as and is defined as L prime of some equal to L of S. Okay. So this is how we get the quotient structure, quotient Kripke structure. Okay. Any questions on the definition of the bisimulation quotient? So what are we doing? We have the given Kripke structure, and in the given Kripke structure, we just see across all the pairs, what are the set of states that are bisimilar to each other, right? And you get a bunch of equivalence classes. Now you merge the equivalence classes, and then you define a Kripke structure with this merged sets, merged classes, right? And the transitions also among these this quotient structure across the merged set of worlds or states, which is defined in this way, right? And you obtain the bisimulation quotient. Okay. So any question before I move on?
No, sir.
No? Okay, good. So now one can also see bisimulation as a game. Why it's a game? Because you see that there is a quantifier alternation. So it's like for every successor on one side, there has to be a matching move in the other side, right? So for every possible move on one side, there has to be a matching move on the others, right? Even though here we are talking about transition, but it's the same. Like when you talk about the labels are being on the states, the idea is the same, right? So I have, for example, like we had this AL of S1, right? Okay, let's go to that original definition. So if we start, like if we consider S and T, right? So if, for example, I consider this particular transition and hence this successor, right? This successor state. So I have to find a match. There exists. So for all possible uh, successors of on one side, there has to exist a successor on the other side, right? So this is how the matching is done. So for example, if I choose this side S1 from the other side, this is the only possibility. So this S1 and T1 has to match. But had there been more successors, some match had to be figured out. Correct? So that's why it is a game. Like, so one guy, which we can call as the challenger, who'd make a move on one side. The defender, who is the other guy, will have to, the other player will have to find a matching move, right? And then the game has to continue. Now, from S, you choose S1, then the other player has to choose T1, right? And so the new, so first we start with a configuration S1, S comma T, and then we reach S1 comma T1, and the game has to evolve. The game has to continue from there. Okay. And now the question is like what I would like to ask you. So suppose the game starts from S comma T. The game evolves to S1 comma T1. So what should be the next? What should be the next move? And the game should continue forever, right? Because this is like a bisimulation relation where we say that, okay, you go to S1 prime, S2 prime, this belongs to R, right? And in order to show that this belongs to R, the game has to continue from here, right? So that's the thing. Or if you consider, let's say, just for the sake of clarification, like for all, if I call it for all S2 double prime, there exists an S1 double prime such that S1 double prime, S2 double prime belongs to R, right? So the game has to either continue from here, or uh, if you had chosen this side, then the defender would have to choose this side, right? If the challenger chooses this side, the defender would choose the other side, and the game has to continue from this side, right? And what next? So what is the idea? Like, so what should be the thing in the next round? How should you play? Is the question clear? Like, so what I'm saying is that, so there is a game, there is an inherent flavor of game here. And how is the game played? Like, so the game, as I said, it's played in round. And now, once I reach from ST, I reach, let's say S1. So S1, I reach, let's say S prime, T prime. Okay. So in the first round, maybe it is the case that there is the challenger chose this side, then the defender has to choose the other side. So the challenger corresponds to the for all player, okay? And the defender corresponds to the exists player, okay? And then the defender managed to match the challenger's move. So, and now we are in S prime comma T prime. Now, how should the play evolve from here? What should be the next thing in the game? What should be the next thing in the game? Again, can somebody say? So the game is now here in this configuration, S prime comma T prime. I call it a configuration. So I have not yet formally defined the game. I'm just sort of trying to build the understanding, and then we'll formally define it. So I started with S comma T, and then the game evolved to S prime comma T prime. Now what? What should be the next thing?
We'll see again choose the side.
Sorry?
We'll see again choose whether S prime or T prime.
Who will, sorry, S prime comma T prime, I did not fully, can you repeat?
Now C will get to choose whether it's for all or there exists.
No, C is the for all player. C is
Okay.
the challenger. So what is the role of the challenger? So the challenger is making a move, and the defender is sort of trying to mimic the move. Okay. So the challenger is making a move every time, and the defender is trying to mimic the move of the challenger. Okay.
Okay. Okay.
Okay. So then again, let me state this. So there are two players, challenger, and then there is a defender. So the challenger corresponds to the for all player, the defender corresponds to the exists player. Okay, exists move. So for everything that the challenger does, what is the for all thing? For everything that the challenger can do, the defender has to match, right? So there should exist something, right? And suppose the challenger chose some successor, this successor. Okay, the challenger chose this successor. The defender may have several possibilities, but the defender chose this successor. So now the game is here ST, the game here is now S prime T prime. Okay, from here, how should the game evolve? Next round, what should the, see, it's a recursive relation, right? So now the game is in a new configuration. Earlier to start with, it was in ST. Now, after this move, the game is in S prime T prime. So now what should the challenger and the defender do?
So now we'll see choose an S double prime. That is a successor of S prime.
C will choose an S double prime.
Yeah.
Okay, and
And now D has to give a corresponding T double prime.
uh, so you are saying that once the game has reached here, you just leave it here, you start from some other successor.
Mm.
Okay, but why is that? Why would you do that? Why would you leave it here and start from somewhere else?
I think
No,
what
no, no. I think S double prime will be
no,
a successor of S prime, right?
Okay, S double prime is a successor of S prime is what you were saying. Okay,
Yeah.
okay. And then here from T prime, it has to find a T double prime.
Yeah.
Okay, okay, fine. What else could have challenger done? Yeah, Rishal, you were saying something.
no. I was just clarifying that. Yeah, that's all.
What
Choosing
else?
from T prime successor T double prime, and then asking D to choose S double prime, which is a successor of S prime.
Right. So you see that there is an inherent symmetry here in the game, which is like at every stage, when you are in S1, S2, at every stage, the for all, there are these two conditions, right? This also has to hold true, and this also has to hold true. Okay. So if for either side, the defender cannot match the move, then the challenger wins. Okay. And when the defender can match the move, uh, it somehow sort of translates to the case that the two states are bisimilar. If the defender can always mimic the move of the challenger, then the two things are bisimilar, right? Because it's like for every move of the challenger, there exists such a transition or there exists such a successor, right? So whenever, so this there exist is for the defender. So if the defender can always match or mimic the move of the challenger, then the defender wins and the two systems are or the two states are bisimilar. But if there is some move of the challenger for which the defender cannot mimic the move of the challenger, then the challenger wins and the two things are not bisimilar. Does it make sense? Like the challenger wins, this means not bisimilar. Does it make sense?
Yes, sir.
Right? So now the other thing is that note that the challenger have these conditions, right? That for all the successors, it can be either from this side or from this side. So at every configuration, right, after every round of the game, so by a round, I mean a move of the challenger as well as a move of the defender, right? So this is a round. So what is a round? A round is like one move by both players, one move by each player, right? So first challenger, then defender. But at each configuration where the round starts, right? For every configuration, so this is what I call a configuration. So the challenger can either choose this side or can choose this side. And the defender has to choose the other side, right? The defender, if the challenger chooses this one, right? For example, this successor, then the defender has to choose this side. If the challenger chooses this side, then the defender has to choose this side, right? Has to mimic the move from this side, and the game proceeds to the next configuration. And see, S1 prime, S2 prime belongs to R, and now you can again start from here. S1 prime belongs, S1 prime, S2 prime belongs to R if they have their successor. So you can see at every round of the game, the defender, the challenger can choose a side. Okay, the challenger at every round chooses a side. Challenger chooses the side in every round. Is it clear why I'm saying that the challenger chooses the side in every round? It's clear, right? So the
Yes,
challenger,
sir.
yeah, okay. So the challenger chooses a side in every round of the game. And the defender has to respond from the other side. So is it okay for everybody? Like why we are saying this, and the game continues forever, right? And if at any point in time the defender cannot respond, then the challenger wins. And the objective of the challenger is to show that the two states are not bisimilar, whereas the objective of the defender is to show that the two states are bisimilar by mimicking every time, right? By mimicking every time. Like, so essentially by showing that for every move of the challenger, there always exists such a matching transition. So if the defender can always respond, then the two states are bisimilar. Clear enough? Right? Any questions so far? Is it okay?
Yes, sir.
Okay. So this is what we say, that the game starts from a pair of states, S comma T, and the two players are challengers. Sometimes it's also called an attacker, and the other player is called the defender. The game is played in rounds, and the configurations are pairs of states. In each round, the players change the current configuration according to the following rules. The attacker or the challenger chooses either one of the two sides, correct? Either the left or the right hand side of the current configuration, and a successor. The challenger chooses a side and a successor. Okay, so if the attacker chooses left, then he has to choose a successor S prime of S. If the attacker chooses right, then he has to choose a successor T prime of T. Clear? Okay, and the defender must provide an answer to the attack made in the previous step. Okay, so this is what. So the challenger is choosing the side and making a move. That means chooses a successor. The defender has to choose the other side and has to make a matching move. Right? And right. So now it says that if the attacker chooses left, then the defender has to choose a successor from some for some state T prime such that the labels are the same, right? A matching move. That's all it says. And if the attacker chooses right, then the defender must play on the left hand side, has to choose again a successor, a matching one such that the labels are the same, has to choose a state S prime. Right, and now S prime T prime becomes the current configuration, and the game continues for another round according to the rules described above. Okay, so you start from S prime T prime, and now so play is essentially this infinite sequence that of configurations that we would get. So that is a play. Okay, or it can be a finite maximal sequence also. If it's a finite sequence, then one of the players would lose, right? Because cannot provide either, for example, in case of a finite sequence, what would happen if either the challenger doesn't have any more a possibility to move, or the defender doesn't have, cannot match the move of the challenger, in which case the defender loses. And on the former case, where the challenger doesn't have a possibility to move any further, then the challenger will lose. But in here, we would assume that all transition systems, every state will have some successor state. So the challenger will always consider to have some possibility to move, right? So if there is a finite play, right, that after which the defender cannot produce a move, that means the defender would lose. For a finite play, the defender would lose because the defender cannot make a matching move. Okay, so but in general, suppose, okay, what can happen is like in a finite play is lost by a player who is stuck and cannot make a move from the current configuration. The attacker loses a finite play only if both S prime and T prime, from which you don't have any action. There is no transition from either the left or the right hand side. But we can relax such a this thing, such a condition. We can always say that our Kripke structure is such that for every state there is some successor. So this condition in that case will never occur. But the defender will lose a finite play if she has no available matching transition, right? So that so as to mimic the attacker. And for every infinite play, the defender would win, right? Because that essentially means that the defender is correctly able to mimic or match the attacker's action. Okay. Right? And a given play is always winning for one of the players, and it cannot be winning for both the players. That's not possible, right? By all the rules here, a play is either winning for the attacker or it's winning for the defender. Okay. Now, this theorem says that, which is not too difficult to see, is like the states S1 and T1 are strongly bisimilar if and only defender has a winning strategy. What does it mean? That no matter what the challenger does or the attacker does, the defender is always able to mimic the move of the challenger. So that is called a winning strategy. So essentially, irrespective of whatever the challenger does, the defender is able to mimic the move of the challenger, right? So it says that the two states are strongly bisimilar if and only the defender has a winning strategy. In this strong bisimulation game, starting from the configuration S1, T1, like where S1, we are trying to check whether S1 and T1 are strongly bisimilar by playing this two-player game, right? And if the defender has a winning strategy, then they are bisimilar, and vice versa. Okay, irrespective of the way the challenger plays, right? For any possible move of the challenger, the defender should be able to move. So that is very important. Like it should not be the case that the challenger plays in a way which is in a stupid way, right? The challenger is also an intelligent player. So the challenger, and irrespective of every possible way the challenger can play, the defender should have a way to win, right? Then the two things are bisimilar. Okay, so now what about, and it says it's already an if and only, so hence we get this, that the states are not strongly bisimilar if and only if the challenger or the attacker has a winning strategy, right? They are not bisimilar if and only if the attacker has a winning strategy. That means at some point of time, the defender cannot mimic the move of the challenger. So now, given these two Kripke structures, starting from S and T, so what you have to tell me is like, what do you think about these two Kripke structures? Are they bisimilar or they are not?
Yeah, I think they
They
are.
are not.
Sorry, so they are not?
They are not. They are not.
They are not. Okay, why do you think they are not?
So the attacker can first go from S to S1.
Okay.
now the defender will choose either B1 or T2. If he sorry, T1 or D2. If he chooses T1, then the attacker in the next move will go to S3.
The attacker will go through S3. Good.
And then there's no equivalent
There's
state.
no equivalent state, right? So it is indeed like you see that the challenger wins here. The challenger wins here because, as Ananya was saying, that you can go from here to here, and the attacker first will choose this side, and the defender will have to respond either this or this. Can respond either of them. Okay. Suppose the defender responds this. Okay. So the new configuration is S1 T1. Now the attacker again chooses from S1, it can go to C, this S3. But now the defender has only one successor, which is like coming to T3, which has B, right? If you see here, the atomic proposition here is C, here the atomic proposition is B. So no way, once the game evolves to S1, T1, the defender cannot respond to this particular move of the challenger, right? And comes here. So you see here that in 2 rounds, the attacker here, the challenger here wins. And but one thing to note here is that in this particular example, the challenger did not really needed to switch sides in the middle. Correct? The challenger did not really require to switch side in the middle, right? It could have been possible. This is also a valid case where the challenger would possibly may want to switch side and play from here in the next round rather than playing from here. Okay, but it was not required. You can in fact construct Kripke structure where you will see that the challenger would need to switch sides in the middle and then continue the play. Without switching sides, the challenger may not be able to win. Okay. So is it clear why these two are not bisimilar? Why they are not bisimilar?
Yes,
Is it,
sir.
yeah, right? But now if you see that set of traces, the set of traces, what are the set of traces these two Kripke structures have? It's like A, then empty, then B omega, then another is A, empty, C omega, right? And similarly here also you have the same A, empty, B omega, A, empty, C omega, right? So you see that both these two Kripke structures have the same set of traces. They have the same set of traces, right? If you talk about similarly automaton, right, where we have instead of uh, the propositions being on the labels, if you had on the transitions, if the transitions were labeled, you would have called it like they are language equivalent. Instead of calling them trace equivalent, they are language equivalent had it been automata. And but these two structures are not bisimilar, though they are trace equivalent, right? Same set of traces, you find them in both the cases. They are trace equivalent but not bisimilar. Trace equivalent but not bisimilar. These two Kripke structures. Clear? Okay. So what you should try to figure out yourself is that can you find examples of Kripke structures where the challenger or the attacker would indeed need to switch side in the middle of the game. Somewhere down the line, the challenger would in fact need to switch side in order to win. Is the question clear? Is the question clear?
Yeah, it's to make sure the symmetry is maintained. Yeah.
I mean, I did not quite understand what you mean by symmetry is maintained.
No, it makes sense. It follows from the definition. Yeah, that's
right? I mean, so essentially the bisimulation game, right, allows the challenger to choose a side at every configuration. For every configuration, the bisimulation game allows the challenger to choose the side. Either the challenger can be on the left side or on the right side in every configuration, right? In every configuration, the challenger chooses the side. Clear? Because that for all was on S1 or on S2 like that. Correct? So, but here we saw that the challenger starts from here, comes here, then the defender comes here, then the challenger would just come here. The challenger did not require to switch side. But it could have happened that the challenger indeed needs to switch side and play from here. Otherwise, would have lost. Clear? So I'm asking you to find Kripke structure where the challenger would need to switch side and then continue the play. Okay. Okay. So we will, is the question clear for everyone?
Yes, sir.
Yeah. Okay. So I'll stop here and we will continue with this in the next class, which is on Monday. And we'll talk about the relation between CTL, the set of, like if two Kripke structures, essentially what we'll show is that if two Kripke structures, they are bisimilar, then they also satisfy the same set of CTL formulas over the given set of atomic propositions. Okay, they satisfy the same set of CTL formulas and vice versa. So essentially, if they satisfy the same set of CTL formulas, then they are also bisimilar. If they are bisimilar, they satisfy the same set of CTL formulas. And if they satisfy the same set of CTL formulas, then they are bisimilar. So this is something that we'll study in the next class. Okay, and maybe you can try meanwhile to construct Kripke structures where uh, the challenger player would need to switch the side in the middle of the play, right, for different rounds. And that is that. And we will also discuss some other kind of relations which are in between trace equivalence and bisimulation equivalence, right? Something called simulation. We'll talk about simulation pre-order and simulation equivalence. So what is a pre-order? What is a pre-order?
Reflexive and transitive.
Reflexive and transitive. Okay, and equivalence is also, it has to be symmetric. Okay, so let's stop here. Any question before we end?
No, sir.
Okay, so tomorrow then we are meeting at 10:30 for the seminar presentation. I will stop the recording.